going to go over the key to the third practice test, and this is the practice test that's the paper practice test that's listed. There's some questions on here that will not be on the exam. So let's begin at the first one. So this one says balance the reaction equation. Now, obviously, I'm working off the key so that you can see what's going on here. But whenever I do these problems, I look for something like here that chlorine is a 3 and this chlorine is a 2. So that tells me straight up, I need to get those chlorines fixed, I'm going to have to multiply 1 by a 2 and 1 by a 3. And now I'm going to check my iron. Right now my iron on this side has 2, so I need to put a 2 here. And since I put a 2 there, I need to check how my OH groups are doing. It makes a total of 2 times 3, which is 6 OH groups. I have 2 over here, so that's why I need a 3 in that position. Now, the way you decide how you're going to write the full ionic is you look for the AQ right here. So AQ, AQ, and then see how this is a solid. This is the one that stays stuck together. A lot of times I'll go ahead and just put a square on it so I'm not tempted. You'll notice over here, I'm putting a square on that. Everything else you break into its parts. Key thing is that you need to remember that if there's a coefficient, it applies to both of these parts, and that when you take something like FeCl3 and you dissolve it into water, you end up with an Fe plus 3, and then you also end up in the water with a Cl, a Cl, and a Cl. So you end up with 3 Cls. So the way you would express a total of 2 sets of those is with 2 of these iron plus 3s and then with 6 Cls, because it's 2 irons and then it's 2 times 1, 2, 3, so that gives you 6 Cls. Same thing over here, so I have 3 BAs, and then because of the 2 I have a total of 6 OHs. So 3 BAs, it's plus 2 because it's the second column of the chart. And then the OH, there's 6 of them. Then I go over here, and again, my 3 applies to both of those things. So I have 3 BA plus 2, and then I have 6 Cl minus once I get to that step. And that is the full ionic. Everything that could be ionic is. Then I need to know the net ionic. Make sure you are very clear on these two. Super favorite test question is distinguishing between the two of them. So the net ionic equation is when you cancel out the things that are the same on both sides. So you can see that the chlorine is the same on both sides. And if for some reason you don't end up with the exact same 6 Cl minus AQs, you probably forgot to carry like one of these 3s all the way through. So you might go back and check and see if you left something out of the full ionic. And then also the bariums are what's the same. And then this is what I leave when I write. This is what I write when I'm done. And by the way, the spectator ions, those are the ones that got canceled out. So they would be Ba plus 2 and Cl minus. Now, here's a balancing problem. So we're going to kind of scribbling it out for the moment so we can start over. So usually a good idea to not start with the oxygen. So I need 5 in front here to start with. And then I'm going to fix my hydrogens. So I need a 5 in front here. So that gives me a total of, I'm going to have an odd number. 10 oxygens plus 5 is 15. So it's going to be hard to get that oxygen to work out properly. Whenever that happens, you erase everything, all the coefficients you did have, and you start with a 2 in front. So you put the 2 in front, and then you're going to fix the carbons with a 10, and then you're going to fix the hydrogens with a 10. And then we're going to double check everything. I've got a total of 10 oxygens, and then I've got a total of 20 oxygens. And so that's why I'm going to need a total of 30, which is 15 O2s. By the way, you should know that this is a combustion reaction. because it's hydrocarbons that are being burned, basically, a reaction with oxygen. Now, our next reaction right here, I would look for the 2, here's my 2, and I'm going to compare it to the 3. So that tells me that I need a 3 here, and I need a 2 here, and then I'm going to need to fix my aluminum, so I put a 2 here. So this is what kind of a reaction? You might be tempted to say synthesis, and that is the correct one. Sometimes people will see something by itself and they'll say, oh, that's a single displacement. But the whole key bit about a synthesis is that it just makes one product. So synthesis. All right, and then this other reaction, remember that you can think of water as HOH. And so here's, if I want to grab that hydrogen, I could, and it only applies to him. So I'm going to put a 3 here, which gives me 3 OHs, which I have here. And then my aluminums are already matched up and my phosphates are already matched up. So this one only needed a 3 right there in front. And anytime that you have positive, negative, of course that is -3, but a positive and a negative something-ish, a positive and a negative something-ish, that's 3 and -1. Positive and a negative something-ish, and positive, negative something-ish. Anytime you have those kinds of situations where every single part has a positive and a negative part, it's a double displacement. The other 2 types that weren't covered were decomposition, and that's where you start with something and it's just one thing, and it becomes 2 or 3. It could become lots of different things, but the key is that you start with something. And then the other one is a single displacement, and that's where you have like A plus BX, and then like you end up with AX plus B. All right, so then on question 3, determine which would occur by evaluating the solubility of the products formed. So this just means that if you know like the phases, so this is kind of a repeat a little bit of the section up here, you're going to end up with, it's however you like to think of it. You could say that the middle ones are together and the outer ones are together, if you like it that way. Or you can say that the positives switch places. You can think of things in a lot of different ways. Or you can keep the negatives in the one spot and switch the positives. But you're going to end up with these 2 products. And you would be told that this is AQ and that this is solid. You'd be told that on the test. And you want to balance it. So I would look for the chlorine right here, and that's why there's a 2 in front of this one. And then the nitrate, we've got 2 nitrates, so we're good, and everything else is balanced. Now, if you make a solid, that means that the reaction will occur. If you end up where everything is like AQ, then it won't occur. And you'll notice that this was actually changed here, and I didn't completely change it. But what you're going to have produced, this would have been AQ. You would have been told all of these are AQ, 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 and AQ. So you would have ended up, I'm going to leave the negatives in one spot, and then I'm switching the positives. And this was lead plus 2, and this is double displacement, so this stays lead plus 2. This is -1, so I'm going to need 2 of these. And then I would balance it. So I'd say, okay, I need 2 of these guys. So that means I need 2 sodiums, and everything else is balanced out correctly. And then you were told that both of these are aqueous. So what that means is that every single piece of this breaks apart into ions. And if everything, like if this weren't here up here, if that were broken apart, if everything is broken apart and there's no solids, no gases, no nothing, then it is a no reaction. And then this one, this is CaO2C2H3 2 plus Mg. Oh, I meant to keep the negatives. Hold on, I'm going to do it where I keep the negatives. So I have I, and then I have O2C2H3. That's acetate, by the way. It has a -1 charge. So this becomes MgI2 because he's plus 2 and he's minus. And then this one becomes Ca with a 2, that's -1 and that's plus 2. Magnesium iodide is aqueous, and so is, oops. And so is this guy. This guy is also aqueous. So again, or aqueous, again, you've produced two things where everything is going to break apart into ions, and there's not going to be any solids on the right. There's nothing left over, so that's a no reaction. All right, now we're moving on to the next one. So we're going to figure out how many moles would be produced from the complete reaction of 10 grams of butane. So notice we only have one number in here, and that means we don't have to worry about limiting reactant. We just got the one train track. So we're starting with our butane. Now you'll be given the mass of these guys, but this is 58.14, so this would have been given. And let's just make sure. So our grams match up, and then our moles match up, and then notice we're going from moles of him to moles of him. Whoops. Moles of him. And that's how we have this 2 to 8 in here. And when you do the math for that, you're going to end up with this 0.688. Let's double check sig figs. So we have 1, 2, 3 sig figs and 1, 2, 3 sig figs. And then on this next question, when you have an amount, remember, so this is 4.90 grams, and this one over here is 14.2 grams. When you've got an amount for each of those, then that means you have to think through a limiting reactant. That means 2 sets of train tracks, right? So we start off, and I always recommend write this number down and write this number down before you get to making up the train tracks so you don't forget where you're going. And this number to be given, normally that would be from the periodic chart. And this would also be given from the periodic chart. Now we're going from moles of aluminum. So there's moles of aluminum, and this is where we're changing. Moles of copper. And notice that the reason we did this change is because there were 3 coppers and there were 2 aluminums. So you do the math. This last number also would have been gotten from the periodic chart. And notice that it has 1, 2, 3 sig figs, so 1, 2, 3 sig figs. You don't even worry about this section, is not for sig figs. And our periodic chart goes to the 100th place, so that it almost always means it has at least 4 sig figs. So usually you can discount those guys. So now we're going to check the other one, 14.2 grams. And we're going to go moles to moles. Then we're going to go right here. Here's our switch of our moles. So in this case, we're going from moles of copper nitrate. Here, sorry. And this is moles of copper nitrate. So copper nitrate. And then we're going to moles of just plain old copper. Then we go from copper until the grams of copper. That's because of the molar mass from the periodic chart. And we double check our sig figs, 1, 2, 3, 1, 2, 3. And then you compare these two numbers and you immediately cross out the one that's too big. You're left with this number. You immediately write over here limiting reactant. This is your excess. And you immediately want to write down the word theoretical yield. Now, we need to know, oh, there's a third part. How many grams of excess will remain? So this is where you take the limiting reactant. So see, there's your limiting reactant. You take your limiting reactant and you turn it into excess, the excess one, because you want to find out how much of the excess was used. So grams to grams, again from the periodic chart, moles to moles, to moles. So again, I'm looking up here. So I'm going from aluminum, that's the 2, and then I have the copper already marked, the copper nitrate. I'm going from moles to grams. And when I do this, this tells us how much was used. I know that I have 490, so I subtract out what I used, and that's how much is left over. And if we wanted to figure out the percent yield, someone would have had to tell you an amount. So like in this example, this is what they collected. So this is the Like if it'll sound like it's in a lab or something like that, a lab setting, it'll say the student obtained, words like that. So this is your actual, and remember this was your theoretical. So you take your actual, it goes on top, that theoretical number over here, it goes on bottom, times 100% is that 72.9. Now you don't want to forget how to do these titration problems. So we have an amount for this H2SO4. So these are actually placed in here. There's this number. This number is the milliliters being converted into liters. And then this number is the milliliters being converted into liters. And then we also know this number, and it's listed here. So again, we have two things. That means that this is a limiting reactant problem. Let's make sure they actually want us to figure out how much product. If it was, then we would need 2 train tracks. So let's read it. It's asking about the molarity of this one. So it's asking us to find out about him. So it's kind of like saying we are skipping the 2 limiting reactant train tracks. We're jumping right to part C for this problem. But you definitely could have enough information where they ask you about, solving one of these 2. So we want to end, because they're asking about this one, we want to end with him. So don't start with his number. Start with the other number and start with the one that's 1 unit. Remember, this is the same thing as moles per liter. So here's my liters here, and I know that my molarity, right here, that's how many moles are in 1 liter. And then I'm going to go, here's where I switch between them. And that's a 1. And this is a 2. Now let's make sure that you got that coefficient when you were looking at it. So again, there's 1. Well, let's just double check the balancing on this guy. So our H2 right here, if we kind of think of this as like HOH, where that's like a group, I'm going to need 2 of those, which affects my OH, which is why I need 2 of these. And that balances out my Na2SO4. You need to pay really close attention on these coefficients. Don't drop them or forget to balance anything. So now we have molarity because we have a mole and we have a liter. If you don't want to put that in the factor label, it's fine. You could have solved you could have solved this problem right here and gotten a mole amount. And then you could have said divided by the 0.03. It's fine. You don't have to have it all like this. Now, because of the change in our semester, we're skipping 7, 8, 9, and 10. And we're starting at 11. So I'm going to write these numbers over to the side. So we have our mass is 5.64 grams. And this is for the gold. And we're looking for C, and we're looking for delta T. I see the C is right here, 0.129 joules per gram degrees Celsius. And then the change of T, let's see, the gold, so it's cold. This is our T initial. So I'm going to do T final minus T initial. And I'm going to say that the final temperature they want it to be is the 25.0. I got to kind of scooch it over. Minus 12.0, and that gives me 13.0, and that is our change of temperature for the metal. It wants to know how much heat will it require to reach that temperature. So here we go, and again, this one happens to be using the S, but we can use the C. So we take our mass, we take our C, and then we take our change of temperature, and I'm going to put this as 13.0. Remember, because when we subtracted, we do it to the decimal place right here. Notice all 3 of these have 3 sig figs, and that's why it's great that that also has 3 sig figs. So 9.46 joules. Notice that the units do cancel. Choop, choop. And, oops. Choop, choop. So you're left with a joule. All right, so next problem. Again, I'm making the list on the side. So we have lead. It's 34.6 grams. And the temperature, let's see, the lead specific heat is 0.130 joules per gram degrees Celsius. And then the change of temperature, so the final temperature, let's see. So this is initially its temperature, unknown liquid at 24. No, the liquid's temperature is that. Let's see, here's the equilibrium. That's the temperature that they both are. So that's the final temperature. And then here's the initial temperature. The initial is 10. Oops, I need to keep these lined up. 104.6. And then I'll go ahead and solve it. 5. So 75.1. Nope, 85.1. No, it's 75.1. Sorry. I'm like doing it in my head to make sure. And then you could, so that's what this value is 75.1. You can just put it all in your calculator too. You don't have to have it solved ahead of time. Then the other part, the unknown liquid, over here, the mass of the unknown liquid is the 30.4 grams. I'm out of room, or I would have did it on the left-hand side. We don't know the specific heat capacity, but we do know the change of temperature is, the final temperature is 29.7, and the initial temperature is 22.4. So when I subtract those, I get 7.3. So again, that's what this temperature change is 7.3. I'm going to divide both sides. I need this one by itself. When I pull out all the math, I'm going to end up with this guy. However, when I did this is 7.3, right? So this number had only 2 sig figs. So my final answer should only have 2 sig figs. It should just be 1.5. All right, question 13. We have an enthalpy change, and it's this number. This is your H of reaction. So that is endothermic. Notice it's positive. That's energy that's going in. So like the energy would be written on that side. How many grams of ammonia would be produced if we have this much heat provided? So this is like the only number in the problem that isn't associated with something. So they're asking about ammonia. So what we know is that we have this many kilojoules, and then there's a 4 in front, right? So that's 4 moles of ammonia. So you take your energy, and then you're going to convert your energy. So you've got your kilojoules, and I know that it's, again, the 4 moles, because there's a 4 here. This is what goes with the whole reaction. If it were per H2O, it'd be per 6 or per 4. I'm sorry, I meant to say that it was because this ammonia is why it's 4. And then we're going to do our moles into our grams. And this is, again, the molar mass from the periodic chart. You'd be given that. And when you solve this problem, you get 182. Check your sig figs. 1, 2, 3. 1, 2, 3. You're good to go. Now, 14. And this is the last one of this type, but there is one problem that it doesn't show, and that's the heat of formation. So make sure, if you need to, go and look in the back of your book for a practice HF formation problem if you didn't get enough in the text or anywhere else, or in the notes. Okay, so what we are given is this equation right here. So this is what we're comparing everything to. And the first thing we want to do is we want to make sure that things are in the right spots. So first I'm going to look at him. Is he in the right spot? Ah, he's in the right spot. That's great. Let's check my CO. Is it in the right spot? No, it's in the wrong spot. But I do know that my water's in the right spot also. So first thing right here for the CO, this down here is the flipped CO. Here's your CO flipped. Oops. So here's the CO flipped. You see how they're flipped? This is now a product. And so we had to take that H value and we flip the sign of it. I think that the math was being done as you went along. So if you're flipping the sign of this, you would get, it's not every step is being shown, you would get 566 kilojoules. All right, so we have everything in its right spot. Now we're worrying about those coefficients. So if you look here, this is a 2, but this is just a 1. So everything has to be multiplied by 2. That's why the second one is rewritten here. So here's a 2, and then this is 5 times 2 is 10. 3 times 2 is 6, and 4 times 2 is 8. Don't forget that your H has to be now multiplied by 2. So it was negative 2219.9, and you multiply that by 2. That's how you end up with this number. And then our CO also isn't correct. So you'll notice that your CO, it was supposed to be a 6, and that's just a 2. So I need to multiply all of those guys. So remember, it's flipped, and that might make it a little trickier. I need it to be multiplied by a factor of 3. So to get from 2 to 6, it's 3 off. And it's flipped. So this number times 2 is 6. This number times, this number times 3 is 6. This number times 3 is 6. And then this times 3 is 3. So we take that kilojoules and we multiply it by 3, and that's how you get this number here. But you can also just put those numbers in a calculator, negative 2219.9 times 2, and then plus 566 times 3. And when you do all that math, you get this one, right